Okay, guys, we've been looking at proportional relationships and situation with proportional relationships. So we want to give this proportional situation a real name, and we call that in mathematics direct variation. This is Mr. Taylor again, and we want to talk about 8.5e. In 8.5e, we're going to do some problem solving that involves direct variation. So let's look at a formal definition. Direct variation is a linear relationship between two variables, x, which is the independent variable, and y, which is dependent variable, that always has a constant, unchanged ratio, which we call k, and direct variation can be represented by the equation y is equal to k times x. So we had said that it was a linear proportional relationship. So that means that the graph will have a straight line. It will pass through the origin with the y-intercept being 0. And again, the equation will be represented by y equals k times x. And also, well, we'll see it a little bit right now, that we can find k by simply dividing y by x. And k is called the constant of proportionality, but it's also called the constant of variation. So we can have two names here, the constant of proportionality or the constant of variation. And we say that when b is 0 in any equation of a line where y is equal to mx plus b, then k is equal to slope, which is m. Okay, so again, when b is 0, so that means we don't have any b in this equation, we'll just have y equals mx. So we call this equation, or should I say we call m k, and the equation takes the form of y equals k times x, which is direct variation. So recognition that when a problem situation has two variables, quantities with a constant ratio, then the variable quantities have a relationship reflecting direct variation. In plain words, one quantity or one variable quantity will vary directly with the other variable quantity. And then we also talked about if we are graphing these particular situations, that we're going to just use quadrant 1. If we are graphing, we're just going to use quadrant 1 because for the most cases it's going to be a real world situation. Okay, now let's get back. The ratio k represents the constant of variation. This is the same thing as the constant of proportionality. The direct variation can also be phrased as a direct proportion or directly proportional. So this ties it back to what we've been talking about the whole while with proportional relationships. In problem situations such as circumference, conversions, unit rates, similarities, and percent involving prediction and comparison with justification is probably the most significant way that we would use these particular direct variation. We will come to this a little bit later, probably unit 8, guys, so let's get ready for that. Various solution methods for solving problems involving direct variation, and we will have 3 in this particular problem, should I say video. We will use a table, whether we're writing a table, and when we talk about horizontal and vertical, we're just saying that x and y can be a table which is straight up and down, which is vertical, or we could have x and y running this particular way, which is horizontal. So that's what we mean by horizontal and vertical. And then of course we'll look at a graph, which is what we talked about here, which is mostly going to be in quadrant 1, and then algebraically, which is y is equal to k times x. Okay, so let's get started with an example. Rachel's parents live in Springfield, Colorado, which is approximately 780 miles from where Rachel lives now, from Rachel's home. If Rachel averaged 60 miles per hour driving, how long would it take her to get from her home to her parents' home? Now let's think about this sentence. And they tells us that they want us to solve this using a table, a graph, and algebraic method. So let's not get ahead of ourselves, and let's first start with what the actual table is presenting us. So I don't want you to pay attention to anything else but the table. And we can just set this up by saying, well, in 1 hour, she's driven 60 miles. Well, in 2 hours, she's driven 120. In 3, she's driven 180. In 4, she's driven 240. In 5, she's driven 300. And in 6, she's driven 360. So you see, we're just adding as we go on. 7, 60, adding 60 is 420. 8, adding 60 is 480. 9, adding 60 is 540. 10, adding 60 is 600. 11, adding 60 is 660. 12, adding 60 is 720. 13, adding 60 is 780. So from a table, we can see it takes her 13 hours, which is X. Remember, time, distance depends on when she drives. 13 will be X, and 780 will be the distance she is to get to her parents' home. So it will take her 13 hours. That's from a table. Okay, so we can take this same thing. Again, we just want to look at it in pieces right quick. So we know we didn't put in the table what we could have easily put in this table here 0 and 0. So if she hadn't started yet, she hadn't traveled any distance, so we can start here at 0, 0 is our first ordered pair. Here's our 160, which we can call our unit rate, our 2 and 120, our 3 and 180, our 4 and 240, our 5 and 300, our 6 and 360, our 7 and 420, our 8 and 480, our 9 and 540. Notice every single answer I get is placed on this line. And our 10 is 600. Our 11 is 660. Our 12 is 720. And then, of course, 13 will be 780. Every single point, here's our X, which constitute our time and the distance, and every single point is on our line. Okay, so this is how we can determine what the solution would be if they gave us a graph. Or just simply go from 0, go up to 780, draw a line straight across, draw a line straight down. Let me do that for us so we could see. So we went up to 720. There's a line going straight across, and then we have this line coming straight down, and it's coming down to 13. So again, we definitely know it's proportional, or should I say it's a direct variation, and the miles vary directly with the amount of time that she drives. Okay, let's take a look at the very last one on this particular one, which is the equation. Now, if you read the problem and read it carefully, one thing that I must preach to you guys that reading is paramount. We must read the problem carefully. And it says she averaged 60 miles per hour. No other constraints and no other information is given us except that it's saying that she have to travel 780 miles. So we can use the equation y is equal to 60x. Then of course we're looking at miles. Miles is on the y-axis, so this will be our y. So we can just substitute, and this is working backwards. So we're going to substitute 780 for y, and that's going to give us 60x. Now we're trying to find out what is the time it took her. The time is x. So in order to do that, we have to isolate x, or should I say get x by itself. So then that's what the author's doing here by dividing, which is the opposite of multiplication, both sides by 60, and we'll come up with x is equal to 13. So in all three cases, table, graph, or algebraically, we are proving that the answer will be 13 hours to travel 780 miles at a unit rate, a constant rate of 60 miles per hour. Okay, and what I have next for us is to test your ability, and I'm giving you a problem, and the problem, actually problem 1, and I think I also have problem 2 as well. So what I want you to do is stop the video, please, and work problem 1. Okay, once you work problem 1, it has section A and section B. Make sure you look at what the problem is giving you and work problem 1 and work problem 1, section A and B, and then when you finish, go on and work problem 2 and 3. Now, if you have any problems with these, please comment me so we can take a look at them, or if not, write these down, and of course you can bring these in for extra credit. All right. Again, we're looking at problem solving using direct variation. This is Mr. Taylor, and I'll talk to you soon.